Welcome to Lecture 2. Let us begin by reviewing the electromagnetic spectrum. The electromagnetic spectrum spans an enormous range of wavelengths and energies. As a physicist, we must clearly understand the scale of radiation that we use to probe the materials. At the extreme, high energy end, we find gamma rays. These have extremely short wavelengths, approximately 10 to the power of minus 12 meters. Because of their very short wavelength, they possess extremely high energy. Moving slightly down in energy, we encounter X-rays. Their wavelengths are roughly 10 to the power of minus 10 meters. Interestingly, this length scale is comparable to the size of atoms and atomic nuclei. This is why X-rays are so useful for structural analysis. Our primary focus in this course lies in the ultraviolet and visible regions. Ultraviolet radiation typically has wavelengths around 10 to the power of minus 8 meters. Visible light lies near 5 times 10 to the power of minus 7 meters. These wavelengths correspond closely to molecular dimensions and microscopic biological structures. This is precisely why visible spectroscopy is powerful for molecular studies. At the lower energy end of the spectrum, we find infrared radiation, microwaves, and radio waves. These have progressively longer wavelengths and therefore lower energies. Always remember the fundamental relationship. Short wavelength means high frequency and high energy. Long wavelength means low frequency and low energy. This relationship will guide our understanding throughout spectroscopy. Now let us formally define optical absorption. Before doing that, we must first answer a basic question: what is light? Classically, light is described as an electromagnetic wave consisting of oscillating electric and magnetic fields. However, quantum mechanics tells us that light also behaves as a discrete particles called photons. This dual nature is known as wave-particle duality. The energy of a photon is given by equation E is equal to h nu. Here h is a Planck's constant equal to 6.626 times 10 to the power minus 34 joule seconds, and nu represents the frequency of light. When light interacts with the matter, three physical processes may occur. First is a reflection, where light bounces from the surface. Second is transmission, where light passes through the material. And third is absorption, where light energy is taken up by the material. Therefore, optical absorption is defined as the process in which material absorb energy directly from incident photons. The absorbed energy does not remain stored passively. Instead, it is used to excite electrons, induce molecular vibrations, and initiate molecular rotations. These microscopic processes form the basis of spectroscopy. Next, now an important question arises: why does a material absorb only specific wavelengths of light? The answer lies in quantized energy level. Atoms and molecules possess discrete energy states. Electrons cannot exist at arbitrary energies. They can occupy only allowed energy levels. In solids, electrons occupy energy bands, mainly the valence band and the conduction band. Optical absorption occurs only when photon energy matches the energy difference between two allowed states. This leads to different types of transitions: electronic transitions, where electron moves to higher energy levels, and vibrational transitions, where molecules vibrate more strongly, commonly observed in infrared spectroscopy. Rotational transitions, where molecules rotate faster, typically observed in microwave region. A photon is absorbed only when h nu equals to the exact energy gap between two states. Consider a semiconductor example. If a photon energy is greater than or equal to the band gap energy Eg, an electron moves from valence band to the conduction band. But if photon energy is less than the band gap energy, absorption cannot occur. The photon passes through and the material appears transparent. Let us visualize this process using an energy level diagram. Imagine a lower horizontal line representing the ground state, that is E ground, and upper line represent the excited state, that is E excited. The energy difference between them is called delta E. For absorption to occur, the photon energy must satisfy h nu equals delta E, or mathematically h nu equals E excited minus E ground. This precise matching condition is a fundamental principle behind all absorption spectra. Every spectral line we observe is a direct signature of quantized energy spacing within a molecule or material. So, in this lecture, we have established the scale of electromagnetic spectrum, the physical nature of light, the meaning of optical absorption, and the role of quantized energy levels. In the next lecture, we will move deeper into electronic transition and absorption mechanism in the molecular systems. Thank you.